Okay, we're back on 2.4 part 2, the product rule and quotient rule, and this is the last problem we left off with, and using the low d high less high d low over low squared, and away we go. There's your quotient rule. So we've got another quotient rule problem here, but we want to find the equation of the tangent line. So find the equation of the tangent to the graph of y is equal to 2x squared minus 4x plus 3 over 2 minus 3x. Now with this one, we've got to first find the slope, and the derivative is the slope. Once we get the derivative, dy dx, in simplified form, then we're going to be plugging in our x to find out, because we'll get a derivative that's dependent only on x. We'll plug in our x value 1 and then find out what the slope is. Then we'll write the equation of the line. So here we go. We're going to do the derivative here. So we have low d high less high d low over low squared. So then we're going to say it's equal to, we're going to say blue, stick with the blue, 2 minus 3x times the quantity 4. We're taking the derivative of 2x squared minus 4x plus 3. So we get 4x minus 4 minus, then we have 2x squared minus 4x plus 3, and then times the derivative of 2 minus 3x, which is negative 3. And then that is all over 2 minus 3x and the quantity squared. Okay, simplifying this further, we get 8x minus 8 minus 12x squared plus 12x minus, and I'm going to put a parenthesis around this, so it's going to be minus a negative 6x squared plus 12x and then minus 9. So then that is all going to be over the denominator, 2 minus 3x, the quantity squared. So now I'm going to simplify the numerator, so I get a dy dx, which is equal to negative 6x squared. Of course, we have the, let me go like this, plus, plus, minus, plus here. Combining like terms then, I have negative 6x squared plus 8x and plus 1. And that'll all be over the same denominator. 2 minus 3x, the quantity squared. And then we want to plug a 1 in. So we've got to get the dy dx evaluated when x is equal to 1. So it's going to be negative 6 times 1 squared plus 8 times 1 plus 1. And that's all over 2 minus 3 times 1 squared. So it looks like we get a slope of 3. So now I have the graph up here, but I'm going to do the equation first, because the equation for the line then is y minus a negative 1 is equal to 3 times the quantity x minus 1. So we end up with an equation at y is equal to 3x minus 4. And sometimes what I like to do is I like to graph the original function, and you see it in red here. So here's my y function in red, and then I graph the tangent line, y is equal to 3x minus 4, and I just want to kind of see what it looks like. You can use a graphing calculator for this. And remember that it should intersect only at one point in this critical region here, at the point 1, negative 1. Okay, that's example 5. Example 6, then we're going to do the same thing with a quotient rule. But the first thing, my first step here is I'm going to do a little rewriting to make the expression a little bit nicer. Guy looks a little happy about this, right? So you'll be happy too when you're taking the derivative without the complex fraction. So we get dy dx is equal to x squared plus 5x. And then we have times 3, the derivative of 3x minus 1. Then we have minus the quantity 3x minus 1. I'm very careful with the use of parentheses, if you notice. And then times the derivative of x squared plus 5x would be 2x plus 5. That is all over x squared plus 5x, the quantity squared. And then we go to simplifying this. So we have 3x squared plus 15x minus, then I've got this product over here, which is then going to be 6x squared plus 15x minus 2x minus 5. Combining like terms there, of course. So, and then that's all over x squared plus 5x squared. So I get the dy dx is then equal to, combining like terms, watch with the plus, a negative, negative, plus, plus. So combining those like terms, you should get negative 3x squared plus 2x, 15 plus 2x plus 5. We have the plus 5, and then that's all over x squared plus 5x squared. And okay, and that's all we needed to do, right? Find the derivative. Then we have example 7. Example 7 I already started using the constant multiple rule. We always want to pull the constant out if we can. And sometimes we're just in the denominator. We get like, oh, is it a quotient? Do we have to use quotient rule? You don't. You pull it out. So if you notice the rewrite I do on the first one, we have x squared plus 3x in the numerator. So we can just pull out that 1/6. Then we get y prime is equal to 1/6 times the quantity 2x plus 3, the derivative of x squared. And then we could just then simplify that as y prime is then equal to 1/3 x plus 1/2. And there you have the simplified form. Same thing if we have y is equal to 5x to the 4th over 8. We can pull the 5/8 out, and then we can take the derivative, y prime, pull the constant out, push it through, and then times 4x cubed, the derivative of x to the 4th. So then we get y prime. Our answer then is equal to, we're going to simplify that to 5/2 x cubed. And there you go. Then for number, all right, I don't have a number on it. The third one, though, we have y prime. And if you notice with that one, I pulled the negative 3/7 out and then divided each term by x and got that nice little answer there. So we have y prime is equal to negative 3/7, and then it's just going to be times negative 2, the derivative of 3 minus 2x. So we get just a y prime is equal to 6/7, a constant derivative, constant slope. So with this last one, we get y prime. If you notice, I made the x squared in the denominator, x to the negative 2 power. So I have a 9/5 I pull out, 9/5, and then I have 9/5, I have negative 2, x to the negative 3rd power. So for an answer, I get 18, negative 18. So I have y prime is equal to negative 18 over 5, and it would be x to the negative 3rd power. So let's take, instead of saying that, why don't we just put it down with the 5 and make it negative 18 over 5x cubed. Okay, that's for that one. And then one more very quickly. With this one, as blood moves from the heart through the major arteries out to the capillaries and back through the veins, the systolic blood pressure continues to drop. Consider a person whose systolic blood pressure, P in milliliters of mercury, is given by this equation. P is equal to 25 t squared plus 125 over t squared plus 1 from 0 to 10, where t is measured in seconds. At what rate is the blood pressure changing in 5 seconds after the blood leaves the heart? So recall that what I said is that we have the derivative low d high. So there's our derivative of the high. Low d high less high, d low here, and then over low squared. So we're just going to find the rate at which the pressure changes here. So we're going to have t squared plus 1 times 50t minus 25t squared plus 125 times 2t, and that's all over t squared plus 1 squared. So we get dp dt is then equal to, when we multiply, we get 50t squared plus 50t minus, then I have 50, do I have 50t cubed? I should have there, sorry. 50t cubed minus, then I get another 50t cubed here, but I want to put that in parentheses first. 50t cubed, and then plus 250t. That's all over t squared plus 1 squared. And then I'm going to cancel here in one. I'm going to plus minus minus. So I end up with these two canceling. And so I end up with a a derivative that's equal to negative 200t over t squared plus 1, the quantity squared. Okay? Now, in this case, we want to know at what rate the blood pressure is changing in 5 seconds after the blood leaves the heart. So we would just say at t is equal to 5 seconds, t equal 5 seconds. Make a little box here. See if I can make it bigger and smaller. So in t equal 5 seconds, we would have dp dt. dp dt is equal to negative 200 times 5. Here's our rule here. Over 5 squared plus 1 squared. And multiplying that out, you're going to get that is equal to about 1.48. Oh, I'm sorry, it's negative 1.48 milliliters of mercury. Let me just do merc, and that would be per second. So that'll tell you how fast the blood pressure cuff is moving. That's about it. My video is getting a little bit long here. You have your checkpoint. You can always check your checkpoint problems if you want to work on those with your textbook in WebAssign. You guys have a great day, and I'll see you soon. Take care.